Okay, welcome to Let's Get to the Marks. This is a video where I'm going through some of the reactions of alkenes, or the most common reaction of alkenes. Okay, it's for A-level chemistry. Let's get into it. So, 1-methocyclohexene and limonene are cyclic alkenes with a citrus smell. That means they smell orangey or lemony. 1-methocyclohexene is manufactured and used in the chemical industry, whereas limonene is found naturally in orange peel. Here we have the skeletal structure of both of these compounds. 1-methocyclohexene reacts with HBr to form two structural isomers. The major product is 1-bromo-1-methocyclohexane. Name and outline the mechanism for the formation of this major product. So essentially, both these molecules, or the one we're dealing with, 1-methocyclohexene here, is attacked by HBr. And of course, that's slightly polar. So the hydrogen's delta positive, the bromine is delta negative. And this is what allows it to attack this compound. So let's have a little look at the mechanism. So first of all, I'm drawing out the 1-methocyclohexene, which has this double bond here, which is an electron-rich area of high electron density. So it's obviously an area that comes under attack. Now, people might make this mistake, and that is that the hydrogen, being delta positive, will attack the double bond, the area of electron density. Of course, we know that positive charge protons don't move. It's the electrons that move, and the electrons are not going to move towards the double bond. What we're going to find is the electrons are going to move from the double bond and attack the delta positive hydrogen. So let's redraw that. And this is the correct start to the mechanism. Although I have to say that double bond is a little bit wonky. So what goes on here? Super. So what happens here is the pair of electrons from the double bond actually move out and attack the delta positive hydrogen. So that's your first mark. And we're going to call this M2 because M1 is the mark for the name of the mechanism. So what's the second mark? Well, hydrogen's basically a group 1 element. It can only have one bond at a time. So it can't have two bonds. So I need to break the hydrogen bond to the bromine if it's to form a bond with the cyclohexene. So that's our second mark here, which I've written M3 for. Now, this is going to form a carbocation, and there's two choices to the carbocation. You can see here the hydrogen has joined over here, and this is for the major product, leaving the positive carbon atom in this position. And this is the more likely position for the positive carbon atom, and we'll go into the reasons for that in the next part of the question. And so we're going to look at the name of the mechanism. Well, because originally our delta positive hydrogen attacked this region of electron density, the double bond, this is electrophilic, and it's addition because the molecule is gaining atoms overall. Its mass is increasing, and that's going to get you the 5 marks, one for the positive carbon, one for the bromine with the lone pair and the negative charge. Okay, and one for the name of the mechanism. Right, 4.2, draw the skeletal formula of the minor product formed in the reaction in question 4.1. Explain what the products formed are formed in different amounts. So now we're going to look at the other option. What's the minor product? Well, the less likely carbocation to form is going to be one where you've got your methyl group at the top here, which we don't need to show in skeletal, but it's going to be one where the positive carbon is over here and doesn't have the methyl group attached. That's less likely to form because it will be less thermodynamically stable. So this is the option that happens when we get the minor product. The bromine ion is going to attack this positive carbon here on the other side of the double bond, but it's much less likely to form. Now, we're actually asked just to draw the skeletal formula, so we just want to attach the bromine here, and that is it. That's the skeletal formula there on the right, and that's worth 1 mark. Okay, but that's the minor carbocation, or the less likely carbocation that forms. Now, why is that carbocation less likely to form than the one in the major product? Well, in product 1, or the major product, the positive carbon atom has more alkyl groups attached, and the alkyl group we're referring to is that CH3, that methyl group at the top. Okay, and that's attached directly to the positive carbon in the major group, in the major product, and so it stabilizes the carbocation, meaning that that route is much more likely for the reaction to take. as the alkyl groups are electron releasing. Some people call them electron feeding or electron donating. So they donate electrons to that positive carbon atom and they make it more stable basically and more likely to form. However, this product that I've shown here, this is the minor product and this is less stable. The reason why it's less stable is because that where I've put the plus there, that carbon atom doesn't have any alkyl groups attached. So it is less likely to form because this carbocation would be less stable. So this is why this one is less likely to form. Now, for those people that are interested in the latest research on alkyl groups, which is certainly contradicts everything that we learn about them in A-level, I'm going to put a link in the description and you can check out some of the latest research that's come out on alkyl groups, which turns up the A-level knowledge on its head. But I wouldn't do that if you don't want to get confused. But if you're interested, go for it. Right, let's move on to the next part of the question. Okay, so let's look at 4.3. Draw the structure of the major product when an excess of hydrogen bromide or HBr reacts with limonene. Okay, so limonene is the second structure we were given in the stem of the question. Which looks like 1-methocyclohexene, but it's just got a couple of extra groups on the bottom. So let's draw that out and then look at what the major product could possibly be. So first of all, we draw out the part of the molecule that's the same as 1-methocyclohexene over here with the double bond here. And then down below, we've got a second double bond coming off at the bottom of the molecule. And this is the limonene structure. So the fact that they've asked us for the major product means they want the one where we get the most stable carbocation formed. And the HBr is going to attack both double bonds. We're going to have addition across both. Why? They've hinted at that by saying there's excess hydrogen bromide. So there's enough to attack all the double bonds. Now, you've got to remember that we've got R groups. Although we don't normally label them, we have alkyl groups. When we're drawing skeletal formula, we just draw them as lines, but they can be methyl or ethyl groups. So the type of carbocations are going to form are these ones where the positive carbon atom is next to the alkyl group. And that's because the alkyl groups are electron donating and they're going to stabilize that positive carbon atom, making that version of the carbocation more likely to form. And so the bromine, our bromine ion, is much more likely to attack that positive carbon atom. And so the bromine is going to appear next to each of those R groups. So when you draw the skeletal formula of the major product, you just want to attach those haloalkanes, you just want to attach that halide ion, to where the R groups are. So our Br is going to attach at these 2 points. Now, the Br is not going to attach at the end of this double bond because that would be less stable, that positive carbon atom to form there. So as it forms here next to an R group, that's where your Br is likely to be. So you need to learn that. And let's get to the marks. I'll see you in the next video. Take care.
You're still here? It's over.